And we are live. So, hello everyone, and welcome to the sixth meetup of TinyML Aspirants Community. We are so glad you are here, and we are joined by a great guest today from ARM, Henry. And so, he will be teaching us some tricks and some stuff about how you can build your own projects using TensorFlow Micro on ARM based CPUs and NPUs. Over to you, Henry.
Yeah. Ooh. Yeah. So, hiya, I'm Henry. I'm an evangelist at ARM, an AI evangelist. So, I sort of help find use cases, work on projects. And today I'm sort of going to try and present some sort of tips that I've learned from doing this, using hardware that's not currently supported, or just like having a checklist about what you do from start to finish on your project, which is good to always have an end goal in sight. So, that's what I'm going to talk about today. So I was originally a data scientist and I've turned into this TinyML world. So I've sort of got a different perspective to it. I'm not just quite all about the embedded world. I know a little bit of both sides. So I'm hoping I can give a view which can help you sort of apply these in the real world. So I'm just going to share my screen and start this presentation. Right. So yeah. So one of the main goals. So this presentation about TinyML at ARM, and one of our main goals is enabling machine learning everywhere. So obviously you know that ARM's in a lot of devices, from smartphones to computers to servers, and it's sort of like at this point now with TinyML you can get machine learning everywhere on every device, and that's sort of like what our goal is, to try and help people get into that position where you can quite easily put machine learning anywhere. So I'm going to start off just with a brief introduction about machine learning, TinyML, from my perspective, how I see them. I'm going to go a little bit into ARM processors, focusing on Cortex M and EFOS-U, just give an introduction to what we're doing in the microcontroller space. And then I'm going to talk about Tensorflow Micro and Simsysnn. And then finally, I'll go into sort of building our own projects and show a few examples when I've done this myself. So yeah, so machine learning and TinyML. So I came from quite a theoretical background when I originally started in machine learning. I studied maths at university, so I sort of got a bit boiled down into the equations behind machine learning and the sort of more boring side to it now, and where now you can sort of like solve real problems. But essentially what I took it as was machine learning is a sort of technique that means you don't have to figure out how to solve a problem, but like hard coding in like if statements, else statements, or just trying to fit parameters to it. It does that all for you. So you have some data, choose like a model that you want, and then from there it's going to try and learn the model to fit to get your output correct. So after that, deep learning, obviously a subset of machine learning. And the main thing I thought about deep learning compared to machine learning is when you're doing a bit more classical machine learning, you don't realize that you spend so much time doing feature extraction, which for me was one of the hardest parts and one of the maybe most tedious, most boring ones. You're sort of trying to find nonlinear representations of multiplying two attributes together, or maybe you're going to square an attribute, where deep learning, that first layer can almost do that, because you've got a nonlinear activation function. It basically solves all those problems for you. You can go straight from input to output, and in the middle it does feature extraction, machine learning, classification, regression. So that's sort of where I saw deep learning was. It was just that step where you can almost miss out the whole like feature extraction part. And then yeah, so now I'm sort of more interested in like what machine learning can do. That was like my sort of theoretical background to it. But really, when you look at ML these days, it's defeating humans in all sorts of areas. So just from image classification, you've got models that can classify images in ImageNet to greater accuracy than many humans can. And then moving on from that, you've got AI models that can play Go and chess and beat like the world's greatest players in Go and chess. And then even further from that, you've got it getting used in the real world of medical diagnosis. You've got doctors who have trained for years. They can have machine learning models help and support their decisions, and they might have an unbiased decision as a AI model because it hasn't got that human bias of sort of maybe taking a risk or not taking a risk. It would view it in an unbiased way and help support those sort of things. And then from there, it's gone crazy. Like there's all sorts of use cases now. And then, as you know, the TinyML is now this sort of like new, sorry, TinyML is this sort of like new step. It's the intersection between embedded systems and machine learning. And this is now what I'm really excited about. I'm really interested in. I've done machine learning on huge servers. I've created models where you don't almost care about the size of it because you're putting it on some massive server. Whereas now, TinyML, it's taking those big models and trying to think like, how can we make them really small, and how can like it be put in like the smallest places or the most abstract places, like in a jungle or something. It's crazy. And then so that last point there sort of covers that as well. Like these days, machine learning models are huge, and they are also taking weeks to create, and they require servers to host them. The GPT-3 model is a prime example of that. I'm sure it trained for 1 to 2 or even 3 weeks, and it's got so many parameters and it's got absolutely billions. So like this is the challenge that TinyML has. Okay, so this is a quote from René and Jem about what they sort of view TinyML to be, and this is sort of like a really good viewpoint, I think, because when I read this, it sort of helps you think of use cases. So AI compute is increasingly moving out of the traditional clouds and closer to where the data is being gathered. This shift is driving huge innovation in AI-enabled hardware and software as designers stretch the boundaries of what AI is capable of. So when I read something like that, I was thinking about these huge image models that we used to have hosted at my old work on servers, and they were just, you couldn't use a little microcontroller, whereas now that's one use case which is pretty much been done quite a few times on a microcontroller now. You can do person detection, you can do like mass detection, you can do all sorts of stuff with images. And it sort of made me think like almost one way you could find a new TinyML project is look at something that's currently in the cloud and is only being solved in the cloud, and try and move that out the clouds, because the advantages are great because you've got more security, it's cheaper, it's faster because you're not having to connect to the internet and transfer data. So situations like that, and the more that we can move out of the cloud into TinyML, the better it's going to be, and it will benefit everyone. So sort of like where ARM sits in this TinyML space is we've got our ARM Cortex M processors, and these are the ones that you've probably used before. They're in a lot of microcontrollers, and they're optimized for cost and power efficient microcontrollers. So they're really energy efficient, and you can leave them running and there'll be little power consumption. We also heavily put ML capabilities into these chips. So we are sort of really wanting to push TinyML. So when we're making these chips, we're designing them around the sort of like huge matrix multiplications that go on in neural networks. They also can be used as a general purpose processor, and coming up with the ARM Cortex M55, we're also going to be including this ARM Helium technology, which is going to greater even performance. Is going to be a new vector processing extension. And then yeah, so the second chip sort of in our ML space is the ARM EthosU MPU, and you'll be seeing these come out maybe in the next few years, I think. But what it is it combines the capabilities of a Cortex M chip. So here we're saying that an M55, an M7, an M4, and M33 can be combined with an ARM EthosU MPU, and it's going to even greater, like, make your ML workloads more efficient. Instead of having to run your ML workload and the rest of your application on the Cortex M, you now can pass over that workload to the EthosU, which has been optimized to run these neural networks. And so the way this works from a developer side like ourselves is it will fit in so smoothly with the production. So it's not like you have to change much about your workflow or edit previous models that you've made or applications. The difference is going to be that we've introduced in this software called the Vela compiler, which is a command line interface. And essentially the Vela compiler, from a really high level view, will take in a TF-like file and output another TF-like file. And what it's doing in between is just optimizing that TF-like file for finding which operations can be passed over to the EthosU, find out which operations have to stay on the Cortex M, and just optimizing that. It even will, like, well, I'll show you on this next slide. So this is the sort of speed increase that we're talking about when you combine a Cortex M55 and an EthosU. So Cortex M7 down here on the far left, and then we're just Cortex M55 with the new vector extensions, the ARM Helium technology, then combining that with an EthosU 55, we're looking at like a 50 times speed from what we're currently doing on a Cortex M7. And then again, the energy efficiency, which is becoming increasingly important when you're talking about TinyML. You want to be able to leave it somewhere for several years and hope that it doesn't run out of batteries. So energy efficiency is becoming increasingly important. As you can see here, the combination is given as a times 25 energy efficiency. And I would just read that as like whatever you currently plan with how long your application might have to stay out on those batteries, you can almost multiply that by 25, and that's the sort of lifespan we can talk about now. And yeah, so I'm now going to just sort of like get into Tensorflow Micro and Simsysnn. So as probably most of you know watching this, that Tensorflow Micro is a specialized version of TensorFlow Lite. It's aimed at microcontrollers. It's been going since 2019, which means like it changes quite frequently, and it's something to keep up with because it's getting easier and easier to use on a daily basis. I will see them pushing new changes to it daily, and it's good to keep up with because something that you might have thought was hard a few months ago becomes incredibly easy when they start sort of like reallocating how it works and everything. So the main benefit of TensorFlow Micro is there's no standard C or C+ library dependencies, which means you're not bringing in any extra memory. Its actual core runtime sits at 20 KB, which, when you think about how you can perform inference on neural networks, the runtime is so small that it will not really add too much to your application. And if you didn't know, you can obviously go and see it on GitHub. It's very well integrated with TensorFlow. You can do a whole workflow going through training models, going into TensorFlow Lite and going into TensorFlow Micro. And yeah, this is actually a really great advantage of it, which I just forgot to mention there. The customizable kernels on TensorFlow Lite Micro is what really makes it stand out, and it's something that ARM with Simsysnn has really been involved in. But if a kernel doesn't exist, it's quite easy to add one in. Or if the kernel exists, but there's a way to optimize that kernel, it's quite easy to do that yourself, or a company like ARM can quite easily do that. And I think that's why TensorFlow Micro really took off, because it allows board makers, software makers to all get involved on this big project that's going to help like benefit all teams there. So talking about Simsysnn and TensorFlow. So Simsysnn, when you create a TensorFlow-like project, you can use different kernels, and we've got a directory in there called the Simsysnn optimized kernel directory. And what you see when you use Simsysnn is a huge increase in speed if you're using an ARM Cortex M processor. This was sort of highlighted when Raspberry Pi had their official port of TensorFlow Micro for the Raspberry Pi Pico. It just improves it massively. It makes it more usable and easy to run. So here's just a few examples of the sort of speed you can see using Simsysnn over the standard TensorFlow Micro kernels. So the hot word benchmark's got a 1.6 times improvement. Speech recognition's got a 4 times improvement, and person detection's got a 4.9 times improvement. And you can think about like how much a difference that can make in a microcontroller. A person detection model taking 10 seconds, you could easily run past the camera in 10 seconds, or even 5 seconds. You could easily dodge it. But if you're speeding that up by 5 times, it becomes a better application. It's being able to run that inference even faster. So it's also open source, so you can take a look at that as well. So yeah, I've now given like a sort of brief introduction into ARM, what we're doing for ARM, the software that's available for TinyML projects. I'm going to sort of now talk about what I sort of do on a day-to-day basis, which is thinking about building TinyML applications and going from idea to solution, and the bits in between, like how you go about that. So for me, I came from a really heavy deep learning background with like knowing all the mathematics and everything, and I would say now it's not even worth getting your head boiled down on that. You don't need to be a machine learning expert anymore, and that's just what I truly believe. The tools are out there now where we want people who are domain experts, not engineers who are trying to beat benchmarks or trying to solve the same problem but even better, or just, you know, there's a sort of situation where you're optimizing the same benchmark over and over, and it's great to see how fast machine learning is being. But for like an applied situation where you're wanting to solve a problem, you may be working for a company, or it's just something you want to do in your own time, the difference of 0.00% increase on a benchmark isn't going to affect the output of that model. It's still going to maybe make the same decision in most situations. So you want to be someone who's almost like a domain expert, like a certain industry very well, or you've got a problem that you want to solve, so you research that problem. What we can do now is you can use these tools that are available. You've got TensorFlow, you've got PyTorch, you've got Keras, which is in TensorFlow as well. You've got all sorts of tools. You've got Edge Impulse as well for TinyML. And these tools now are just changing you from being someone who had to spend hours researching, making a model and everything. You can test out ideas quite quickly. You can find data, see if it's going to do anything. You can try different models. It's all there. There's no sort of coding in anything. You can just sort of like a few lines of code to test out one idea, a few more lines of code, test out another idea. And that's sort of what you need now. You need that problem. You don't need to be able to do the machine learning anymore. You need the problem that you want to solve and the data. So what I'm saying here is take advantage of the available tools. Machine learning is domain experts or creative people, not just engineers. And it's so true. I've come from engineering side. I've come from like being a part of strategy and consulting, and it's how machine learning is used in the real world is the people who solve problems want to use it as another tool in their tool belt, pretty much. Like they've maybe gone through the statistics, they've had a look at different solutions that are currently available. Machine learning should just be a tool they can pick up and throw at their problem and see if it's a workable solution. So just some ideas about what TinyML can do for you is improve healthcare through wearables. It keeps data secure, and this is one that I'm going to keep going on about today, I think, because I find it really a great part of TinyML is you are not sending data to the cloud anymore. It's not just going for whoever to see, or maybe there's some sort of a server could break down and data's lost. For me, that's one of the main parts. It can stop machinery breaking down. You can throw it into a factory, a TinyML project, and leave it there for weeks, and you don't need anything else connected to that. It maybe just sends off a signal once something breaks or something. And of course, many more parts to TinyML. So this is sort of what I'm getting at today. Is I've come from a data science background, and I've done this from not just TinyML space, and I've got a data project checklist here, which I'm going to try and go through with everyone, which has been adapted from Jeremy Howard from Fast AI, who's been like quite a big inspiration for me in data science as well, because he's all about making it available to everyone. So your data science project checklist is got a few parts to it. So strategy is what I was saying before. What are you trying to do? Is there something you can improve on? Is there a problem that you've spotted at home or at work? Is it something like someone's mentioned to you and you think machine learning can solve that problem? That you have to have this problem out before in front of you to be able to solve it. You need to know what data you need. You're going to need to know like if it's been solved before, if there's alternatives to this problem. The second part is data. Is the data available? Which obviously in machine learning, like if you haven't got the data and you've got no way to collect that data, you're going to really struggle to ever come up with a model, and you're probably going to need quite a lot of data to solve like quite an original problem. So is it available online for free, or can you buy it somewhere, or can you capture the data yourself? It's something you're going to have to ask at some point, and you're going to need quite a lot as well. So it's something you've really got to think about. From is the data good? Is the data is it enough data? Is the data biased? That sort of stuff, and that sort of falls into the next part, analytics. So what kind of insights can you find from the data? So now you've got that data collected, you know what you're solving. Is there anything you can look at? Can you take a quick glance at that data, or can you analyze it heavy and almost like see some sort of correlations, maybe see bias in the data? Maybe you can see that like the data actually there's some data that is almost like repeated in the data set, and it's like not adding up correctly. There's a lot of insights you can find from the data that if you don't look at it from the start, it will become a big problem when you try and look back at why your model's not working, or why is it overfitting. So it's a really great point to just look at it from the beginning. What analytics are there? Could you perform like quite a simple linear regression on your data and learn anything from that? Because if you can't fit quite a simple model to it, you might really struggle to fit a really complex model to it. And then implementation. So I guess in TinyML, it's sort of like what board are you going to use, what backend are you going to use, what hardware like sensors do you need. But if you're looking at this from just a general data science perspective, what like capabilities do you need? Do you need to be able to make a server? Do you need to be able to write like C code? Do you need to be able to create a custom model? That sort of thing. then the next step is maintenance. So what systems are in place to track changes in the operational environment? How can you update your model? So what I sort of mean from this point here is, if you're putting a TinyML project out and you're just leaving it there, sort of not paying attention to it and just hoping that you'll get some sort of signal back at some point, how are you going to know when that has stopped working? So, for example, if you've trained a TinyML model to recognize faces, but in all of those pictures, they were in the sun, and then when you deploy this TinyML model, it turns out it's in the shade. How are you going to sort of like track to see, right, this model's not working? It's recently changed, like maybe the sun's changed direction. Like, how are you going to be able to spot those? Is there anything you can do in your model to try and like adjust to situations like that? And then finally, constraints. So when you look at those points there, what constraints need to be considered in each of the above areas? So you might have a constraint on data. You might have a look at the analytics and realize that this might not be possible, sort of thing. Implementation, you can obviously think of constraints in that, like maybe you would struggle to build this yourself, sort of thing. So here I've sort of adapted, I've taken that checklist there and done it to a previous project of mine, which I did at a previous company. But so this is quite an applied project in engineering. So I'll just give quite a brief overview. So in engineering companies, they have quite a strategic view on their assets. So they don't want assets to deteriorate and become unusable, that sort of thing. So the way it was sort of done for a while, and it probably is still done in a lot of places like this, is someone will go out and investigate that asset, and sometimes that the data doesn't already exist for that asset. They've got to try and do the whole research, figure out all the different information about this asset. So thinking about like this sort of strategy here it's a lot of work for an engineer to go out, look at a pipe, for example, or some sort of concrete, and try and age it, try and get the material, try and just state all this information about it. So the sort of idea that I came up with in this situation was an app that will start helping an engineer fill in that data just from an image. So we already had this data set because we already had engineers going out and writing about what they thought about assets. We had like a big set of data there from previously hand input data. So so the analytics that we got from there is we learned that some asset types had more information, which could then lead to bias in the data. Certain assets, like people, it was impossible to age just from looking at it. So if you didn't have previously available information, you couldn't do that. So then you got to try and look into that and think, well, how are we going to try and fill that in? So for example, with some sort of materials, you can be like, well, actually, we stopped using that material in water pipes because we found out it was really bad. So we know that it's somewhere between the 20s and 60s, sort of thing. And then that can really help a model learn. If you can put like sort of like your own domain knowledge into that data, your model is going to learn a bit more. Otherwise, it's going to try and fill that in itself. Implementation. So here, I was looking at this from a phone app perspective. So you would be able to take the picture right there, run the model, and it would get the output. So the camera just on an iPhone or an Android phone was going to be fine for this this example here. So maintenance. So for me, the way the maintenance was going to work in this perspective, and this is maybe quite a unique perspective, but in my head, once this app's been deployed to engineers, they're going to take this picture, it's going to fill the data in, and they're going to check that themselves. So it's almost like a contained situation, they'll probably correct it, which then creates a better data set, and further updates the model later down the line when you can take that. And then constraints. The main constraint that I had in this project was you sort of had to make the assumption that all assets have the same attributes. If you want to build this big data set, you're going to try and have all the same attributes, which in the real world isn't true. Like, some assets aren't going to have information for some attributes, and some assets are going to have loads of different attributes, and some will only have a few that people are really bothered about. So you've got to try and meet in the middle of where's the best coverage of all different assets. So it's sort of like something you've got to really do in data science is look at, like, right, can we get it all, or should we just try and get the best solution possible? And that might be the way to go in some times. And then the result of this app is saving hours of engineers' time from doing, like, for someone who's an engineer, it's probably one of the most boring parts of your job is looking at old assets. It's not really like you're solving a problem. So this was great for engineers. They're saving hours of time. They're just, half of it's filled in. It's almost just like a check for them. So yeah, some tips about working on data science projects, and this really comes down to, maybe this is just me looking from my perspective, because when I first got involved in data science, I was awful at this sort of stuff. So it's really great to, I think, just get people on it early. Like, if you're starting a project, document your work. It needs a README. You need to clean up your code. You should maybe include comments in your code, an installation guide, so people actually know how to use your application. And finally, like, example usage. Like, it's all great having, like, some life-changing application online and no one knows how to use it, or they've never seen it used, so they don't know what it does. So these are the sort of things that you need to think about from the very start of your project. Like, documenting it is going to make it that whole much better. It's going to take it from being just some code online to a full TinyML solution that people can use and put into the real world. And they don't have to be too in depth. You can keep it quite simple. It's just, it has to be there. Your code can't really explain itself, if you know what I mean. And yeah, so when I moved into TinyML and started working on projects like this, one of the main things that you don't really think about when you just come from a pure data science background is you've got to really be aware from start to finish. Like, you've got to know what sensors you're using, what board are you using. So for the application plan here, what board and microcontroller will work for this solution? What sensor will I need? And is everything compatible? So you might get all the way through this app, try and test it on maybe like a board you've got, and you might not have a compatible sensor, or you might not have the right sensor. And you've got to really think from the start, what output am I going to get from my sensor? And how can I use that then when I'm making this model? Pre-processing. So one of the parts of data science, and I mentioned earlier that deep learning can cut out that pre-processing. When you get on microcontrollers, you sort of are also trying to reduce the size of that neural network. So you do need to do a bit of pre-processing. But if you're doing pre-processing that isn't already available on a microcontroller, so maybe if you're doing some sort of signal processing that you can quite easily write in Python, and then it comes to trying to implement this on a microcontroller, and you can't do that pre-processing, then the model is going to be, you're going to be unable to put your data into that model. And this is something like I learned, because when you're using TensorFlow in Python, you can quite easily just import a function, transpose the data, do all sorts to the data, and before you realize it, you're not going to be able to do that on a microcontroller, because it's hard to code yourself. And then also like what data types and data sizes are acceptable on your microcontroller. How much memory does it have? What can it use floating point numbers, or is it just stuck to integer numbers? And then model development is quite important on TensorFlow Micro, especially because there's not all layers available. So the big one for me is like I used constantly batch normalization, and it's something that's not available on TensorFlow Micro. So you have to, when you're writing that model, know what layers you can and can't use, because if you train that for a day, maybe 2 days, or even just a few hours, and then you realize it's not deployable, you're gonna have to start again from scratch essentially. Another good point here are the models I can use for transfer learning. So this is something that I cannot stress enough in data science, is someone's already probably done something quite similar before, and it is worth taking advantage from that. So image recognition has been done so many times that your new use case of image recognition might be quite original, but when you look at these models and you analyze these models, the first few layers of an image recognition model is looking at the sort of edges in a picture, or like the lines in a picture. It's not looking at the actual object in that image until further on in the model. So when I say transfer learning, you use this model originally and you try and freeze the very start of that model and then just train the end bit. So it because you don't want to try and recreate the wheel sort of thing. Like, it's already been done. You might as well reuse the work that's been done, change the head of the model so it just classifies your very specific situation. And then finally, like, is this model too big for a microcontroller? Really important, obviously, because most models in deep learning are huge, and most of them won't fit on a microcontroller. Even if, so you could come up with like a really groundbreaking solution, a big neural network, and then it's going to be huge and it wouldn't fit on your board, for example. And then it almost, you get to that point and your solution's not going to be able to work in that situation. And evaluation. So I put here, do we need near perfect accuracy? You obviously are trying to get near perfect accuracy, and you're trying to evaluate how well your model works. Like, is it biased to certain inputs, or is it only 50% accurate, or does it not work in certain daylights, sort of thing? You need to think, though, when you look at all that as well, do I need near perfect accuracy? Is this TinyML model, is it going to make too much of a difference if it's 100% accurate or 80% accurate? When you look at the MicroSpeech example in TensorFlow Micro, they accept a lower accuracy so they can have a smaller model that can be deployed on a microcontroller. And you have to sort of balance that out. Like, you're not going to be able to get the most perfect model ever on a microcontroller. So you need to judge where is it acceptable to work. And then just the training workflow, because it's sort of, I've not really, it's been covered quite a bit, but it's sometimes I think a little bit overlooked about it's not just the same as any data science workflow. There's a few other steps to it. So you've built your initial model architecture, you've trained your model, and then you've tested your model. After that, you can then take that even further. So you can start to optimize your models. So there's pruning, which is taking out neurons from the model, which maybe are not having much influence on the output. So maybe it's constantly outputting a 0, so it's not doing anything, or maybe it's really close to 0. So if you take it out, and it affects your accuracy a little bit. There's weight clustering, which is something ARM does quite a lot when they're trying to really optimize some models for the model zoo, is they do weight clustering, which means you've got a lot of different weights in your neural network, but like maybe loads of them are quite similar in value. Is there like clusters of numbers we can find that can represent those floating point weights, or those weights that are just 1 or 2 numbers away from being the same weight? Can we sort of cluster those together? And then you're only sending so much data into your neural network. It sort of can unravel those clusters and use them in the certain parts of the neural network. And then quantize aware training. So this for me is almost like the final step each time. So you've pruned it, you've done some weight clustering. You might as well just train it for a few more epochs where it's aware that it's going to be stuck in. So if you're doing in 8, for example, if it's an 8-bit integer, you're going to want it to like try and find those numbers that best work in that data type. So quantize aware training is just like a final step, just to improve the accuracy instead of just assuming it will stay as accurate on a lower data type than your floating point numbers in training. And then once you've done all that, you're going to then convert / optimize your model for TF-Lite. So that's just your TF-Lite converter. You're going to like pick your inputs and outputs, like data types. You're going to pick if you want to add any other operations on the ones that are currently supported. You pick a representative data set at this point to help the model find the ranges of numbers that will be seen. And then finally, once you've done all that, you can then retest your model, because this is now going to be different to what happened during the original training. When you're doing your original training, you're solving it, you've got 90% accuracy. You want to try and keep it as close as that. So you need to go through these extra steps just to make sure your converted model is right up there. So yeah, just a quick list of helpful tools here is TensorFlow and PyTorch. For TinyML, obviously more TensorFlow, but if you're like me, I really love PyTorch. And when I first used, it took me a while to test out PyTorch, but when I did, for me, PyTorch is quite easy to come up with an idea, and then you later maybe try and implement that in TensorFlow again. But those two tools is really up to you which one you pick. Obviously, TensorFlow's got the micro support. Then there's Edge Impulse, which is really good as well for testing out ideas. TensorFlow Micro is what I base most of my TinyML projects on. Simsysnn and SimsysdSP. So I didn't cover SimsysdSP, but essentially like these are libraries that ARM provides when you're using ARM Cortex M processor. Simsysnn is going to speed up your neural network processing. SimsysdSP is for your digital signal processing. So if you know that you need to maybe take audio and convert it into a spectrogram, SimsysdSP's got some optimized functions for that, which you can do then on a Cortex M, and it's going to run really efficiently. Micro TVM is something I'm really excited for. So that's currently in development. TVM is doing really well, and then they're trying to get this micro TVM out. And in my opinion, it will be a really good tool, maybe in combination with the other tools, but it's going to hopefully allow for more deployment because you're compiling models in instead of using an interpreter. And then finally, we just got 2 bits of ARM software. So we've got MBedOS and ARM Kyle MDK, and those two just sort of give you they're like sort of like development environments that are going to really just help you prototype on ARM. Essentially, like they've got all the tools and optimizations built in that you can then use on your projects. So here I've just got a little example of so something I've not really covered up until this point is one of the things about TensorFlow Micro and a few of the other libraries is there's very specific boards that are supported, very specific like sensors that are currently supported, and I'm trying to say like don't let that get in your way here. So you might be limited and you might not be able to get the Arduino Nano or the SparkFun Edge or any of the other supported boards. You might be stuck on a project and you need it on a very specific board that you've got, or a very different external sensor that you're needing to implement here. So what I'm trying to showcase here is how you can just adapt those applications that they provide in TensorFlow Micro for your own different boards. You don't have to rely on them. They've given you example code, and it's quite easily to use most of the code and just adapt like certain parts of it. So an example here is I've got the wake word application working on the Raspberry Pi Pico, and the way I did that was so yeah, the benefit here is a less than $10 wake word. Like, you're not having to buy an expensive board there. Like the Pico itself is about $3 or $4. The microphone I use, which is an Adafruit electric microphone, was about $5, I think. So you're looking at like less than $10 there, instead of maybe buying a board that's a bit more expensive. And if you're creating a few models here to work maybe around your house, or maybe you need a few to work in the real world, like maybe you do need to try and come up with this custom version of wake word. So I'm just going to explain like what I did here to get that to work on the Raspberry Pi Pico. So I've just saying the tools on the right here. I've got the Raspberry Pi Pico, the Adafruit electric microphone, Tensorflow Micro, and also Simsysnn. So there's a little video here. So I've recorded a video because I've got an accent that doesn't get picked up on the MicroSpeech example. So I'll just play this to you quickly. So yeah, in case you didn't see it, everyone's seen it before, but essentially the word yes was said and the Raspberry Pi Pico's light turned on. So how did I do this? So this is the hardware setup. So I wired up this Adafruit microphone amplifier to work on the Pico, and there's just a quick diagram there in case you want to do something similar yourself. And then I looked into the MicroSpeech application. So as I was saying before, they've provided a lot of applications, and almost any use case that I can think of, there's a baseline there pretty much that you can build off on. So you've got person detection, you've got MicroSpeech, you've got the Magic Wand one. So you can just almost think about how many different applications you can make from those starting points. So here, the changes that I had to make for MicroSpeech to make it work on a currently unsupported board was the audio provider, which just connects the device's microphone hardware to the application, and the command responder, which is like what it does with the model's output. So in this one, it just turns on the LED when it hears a spoken word. So yeah, so do it yourself. I've got a link at the end for like the code, and I did a Hackster blog on this to help people sort of like understand the decisions I made. But I sort of like had a little bit of an in-depth look at the Tensorflow Micro examples, read the TinyML book, and you sort of get the gist of what each part's doing. So what I figured out about the audio provider was you need a microphone that's constantly on, collecting data, and then while that's collecting data, the neural network's being ran on the previously collected data. So like I said earlier, I'm not from an embedded background, so I managed to get it to work. So I'm sure many people can do this, and they can maybe improve on my work. But I was reading through this, so then I read through like maybe the documentation of the board as well. So I found out that like the best way to do this on a Pico would be you would be collecting the data from the microphone and then adding it to a ring buffer, and then that ring buffer is just slowly updating each time data is collected from the microphone. The way this works, so you can have your CPU doing other stuff, is you use a DMA there to push the data straight from the microphone into the ring buffer. And that, for me, felt like quite complex at first, but like once you get that basic idea down, study it a little bit, you can really just make these applications work on any bit of hardware. And then the final bit, command responder, this one's like really up to you. Like you can really adapt that to do anything you want. So the microphone, you obviously need it to be collecting data and put into the model as they use it. The command responder, like you might want it to say something back. You might want it to, if you're talking to it, you might want it to like move something, or I'm not sure. That's completely up to you. So on that one, I just got it to flash the onboard LED, which is a bit boring, but you could get it to do something so much more fun. Like a great example actually there is turn on. You have something like a Pico, which is like $3, hardly using any energy. You say something to it and it turns on a more expensive piece of hardware, which then will do like a more complex analysis. And there's a great example of someone who has a Pico that has a motion sensor on it, which turns on a Raspberry Pi, which then detects someone's face. And that's like sort of one good use case of like a command responder. So yeah, here's the source code for the Picowake word. So I've got the GitHub code if you want to do it yourself, and I've also got hacks if you want to have a look at like a bit more in depth about how I sort of like came up with the solution of going from just example application to final application. And then finally, this is the last slide from me, and this is just a few other resources. If what I've said to you today has made you a bit interested in ARM, we're really focused on TinyML and AI in general. I don't know if you've all seen the ARM V8 release recently, but you could hear on the videos the focus on AI, and it is going to be important, not just for ARM, but for the whole world. And ARM's really involved in that, and the TinyML space with Cortex M and Ethos U55 is going to really enhance your models and improve your inference times. So we've got something called the AI Virtual Tech Talks, which is on it's on every fortnight. I think it's on a Wednesday or a Thursday. You can find out more information there, but essentially what we do is we have a look at our AI partners, sometimes internal talks as well. So I've done a workshop there about using some of our software called PyArmorN, but we get like AI partners in as well who talk about their product and showcase what they've done, how they've used ARM to make it even better, sort of thing. And it's really interesting to know. And there are some really cool AI startups coming out, so it's quite interesting to see what people are doing with TinyML these days. And then finally, we've got the Innovation Coffee podcast, which you can find on the ARM software developers YouTube. Again, that's sort of like similar. It also focuses quite a bit on IoT as well as just TinyML, and there's also like all sorts of ARM related stuff on there. But like for example, today they've got Raspberry Pi on, and they're going to be talking about TinyML and the Pico and the future. And previously we've had all sorts of guests on, from SparkFun, sorry, to I'm trying to think now. I've gone blank. Arduino, I think. But yeah, so we've had all sorts of guests on there. So it's really great to sort of listen from industry leaders, but also little companies as well. It's more of a conversation than just a presenting of work. Like you get to ask them questions. You get to learn about their story instead of just about their product. So that's all from me today. I hope that was helpful for everyone. And I hope you can start working on your own TinyML projects.
Yep. So I will just check back if there is anything or any questions left out by the folks.
Okay.
So nope. It seems like that. Questions. Cool. Nice. Anything more from your side?
No. If no one's got any questions, I just hope I've got some inspiration to work on their own projects.
So I guess we can wrap up here today. So thanks everyone for joining this webinar for this session. And this was truly a lightning session by Henry. And I guess every one of us learned some things from him about making projects using TensorFlow Micro. And yeah, that was it. Bye-bye.
Bye, thanks.